Hi everyone, welcome to this geometry tutorial video. Today we'll be talking about Chapter 5, Section 7, so please open your textbooks to page 348 and follow along. While you're watching this video, please take notes and examples down. So we know that we can relate the sides of a right triangle through the Pythagorean theorem. The Pythagorean theorem we know is a squared plus b squared equals c squared. So let's do an example using the Pythagorean theorem. This example most of us have seen. We have a triangle that has legs with length 3 and length 4, and we want to know the length of the hypotenuse, the longest side across from the right angle. So we're going to use the Pythagorean theorem and plug these side lengths in to solve for c, to solve for the hypotenuse. And that's what we've done right here. We have the Pythagorean theorem, we've plugged in 3 and 4 as the side lengths for the legs, as for a and for b, and we want to solve for c. So when we square 3, we get 9, and when we square 4, we get 16, and when we add those together, we get 25. And to find c, we need to take the square root of both sides to find just c, not c squared, and c equals 5. And most of you all know this as a 3, 4, 5 right triangle. This particular set of numbers, 3, 4, and 5, is called a Pythagorean triple. It is a set of whole numbers that satisfy the lengths of a right triangle. Now, there are other Pythagorean triples out there. There are 6, 8, and 10. There are 7, 24, 25, 24, 25, just to name a few. 3, 4, and 5 are the smallest set, the smallest Pythagorean triple. Now, let's turn our attention to an example where we're not going to get a Pythagorean triple. We're not going to get a whole number for one of the side lengths of our right triangle. So I've set this problem up right here. We have a right triangle, and I've labeled the sides A, B, and C. So of course we're going to use the Pythagorean theorem, and I've plugged in the side lengths for each of the legs and the hypotenuse of our right triangle. And we want to solve for x. So what we're going to do is go ahead and square each of the values that we have a length for. So we have 6 squared is 36 equals 144. And in this case, we're trying to solve for one of the legs. So we're going to isolate x by subtracting 36 on both sides. And we get x squared equals 108. So when we solve for x and take the square root of 108, we know 108 is not a perfect square. So right now, we want to figure out if this is actually the simplest form we can express x. And the answer is no. So let's go ahead and figure out how we can simplify this radical. Now, the steps that I want us to take for simplifying radicals are this. We want to factor each radical, so factor the number under the square root until we only have perfect squares and prime numbers underneath the radical. I'm going to show you what that means in just a second. Once we've done that, I want us to take the square root of each of the perfect squares, and then with the prime numbers we have left over, if we have multiple prime numbers, I want us to multiply them together underneath the radical. Those prime numbers will stay underneath the radical. So let's go back to we have x equals a square root of 108. So let's go ahead and simplify this radical to the simplest form we can. We're going to go ahead and factor this, so that means break it into numbers that multiply to equal 108. So the numbers that do that, the first perfect square we get is 4. And 4 times 27 equals 108. So that's great. We have a perfect square in 4. But 27 is not a prime number, so we're going to keep factoring 27 and see, of course, we can pull out another perfect square, 9. And in this case, we have 2 perfect squares, so we can stop with them, and then 3, which is a prime number. So now step 2 is we're going to take the square root of each of the perfect squares. So when we take the square root of 4, we get 2. And when we take the square root of 9, we get 3, of course. And we take those outside of the radical, because we just took the square root of them, obviously. And when we have 2 of them, we're just going to multiply them together. So we have 2, which is the square root of 4, and 3, square root of 9. And we have both of those outside the radical. And then we have 3 left over inside the radical. So with this 2 and 3, we're going to multiply them. 6 times the square root of 3. And that is the value of x in its most simplest form. Okay. So let's do another example where we are trying to simplify radicals. In this case, we want to add two radicals together. Now, properties of radicals we want to remember are that radicals, we can kind of treat them like a variable in the sense that we can only add radicals together if they have like terms. So let's look at this case. We want to add together 2 square root of 12 plus the square root of 27. The only way we can add those together is if we end up with these values having the same number under the radical. Let's see if we do. Okay, so when we simplify 2 square root of 12, we get 2 square root of 4 times 3. And this 2 is still outside the radical, so I've just factored 12 into 4 times 3. And I can take the square root of 4, which is 2, so I brought the 2 outside of the radical. So we still have this 2 from the beginning, times 2. And square root of 3. 3 is a prime number, so it's going to stay inside the radical, of course. So when we multiply 2 times 2, we get 4 times the square root of 3. Okay, so square root of 3 is this number inside the radical. Let's go back now to the square root of 27. When we factor 27, we get 9 times 3. 9 is, of course, a perfect square, so we're bringing 3 outside the radical. We take the square root of 9. And so we have 3 times the square root of 3. So we have two numbers that have the same number underneath the radical, so we can add these together. And all we're going to do is take the number outside the radical and add them together. It's just like adding 4x plus 3x. And instead of x, we have square root of 3. So it's going to be 7 square root of 3. Okay. Let's take this and do our last example. So I've given you a triangle, and it's not, this big triangle ABC is not a right triangle, but we can draw an altitude from B down here to form 2 right triangles, actually. And the question I want us to answer is, what is the sum of the length of AB and BC? So AB, what's the sum of this length plus the sum of this length? So what we needed to do is solve for the hypotenuse of each of these right triangles. So the hypotenuse here is a square root of 306 after we've done the Pythagorean theorem. And the same thing over here, square root of 306, because we're using the same values. So we got the same number. That makes sense. Okay, so let's go ahead and add the radicals. So we have square root of 306, square root of 306. And by what we just looked at, I can add these together since they have the same number underneath the radical. So I get 2 times the square root of 306. So I'm going to factor 306 into perfect squares and prime numbers. And the factors that I get are 4, 2, and 17. Okay, so 2 and 17 are prime numbers. They're going to stay inside the radical, but 4 I can take the square root of and bring outside. So I get 2, which is already outside, times 2. Sorry, my pen. Times the square root of 2 times 17. And 17 is underneath the radical there. Okay, so we're going to multiply these two numbers together. Equals 4, just 2 times 2, times, and I'm going to multiply these prime numbers together. 2 times 17 is 34. Okay, so that is the sum of the length of AB and BC. 4 times the square root of 34. Great. So let's review. What we've done is reviewed the Pythagorean theorem, looked at a few examples of Pythagorean triples, and mainly we looked at simplifying radicals and then adding radicals. Great job, guys. Thanks.